3/4.
He's far from
I'm tall. By 3/4.
You look taller than you actually are.
Oh, I know. It's a huge step. Big sleep. He did want to hit us. That's on tape.
Good one, hit you next time. It's gotta be
He wouldn't want to hit me because I'm doing well in his class. Doing so well. Matt, what's your percentage like? Oh, that's weird. What do I have?
95.
Yeah.
Oh, you do?
Just as I'm telling you,
Taller than both?
what do you mean how? You actually have dumb.
Position is
No, it's not. I thought you did that. You call yourself?
No, I think, but I think what I've been able to do this semester is weird because it's not like I'm growing my brain. My brain is against it. It's nice. It feels nice. I can feel it.
Okay, good morning everyone. So we're going to solve a problem today using the Mohr circle method, and I hope you've had a couple of these examples during recitation. So we will see how we apply it for a combined loading problem. Right? I've uploaded the pre-lecture notes, PDF and the note format. So I'm going to make use of the figures that are there on there. I'm going to draw them out first. Okay, so here is a problem. So we have a shaft which is 2 meters long and has a certain radius given to it. Okay, so the radius of the shaft is 22 meters. So R 20 millimeters, and the length of the shaft is 2 meters. The back end of the shaft is fixed to the wall. Okay, and then there are forces which are acting on the front end of the shaft, the free end of the shaft. As I said, at least because this is material that we are developing towards the end of the semester, I will be giving you the axes as we solve these problems and in the exam as well. Okay, typically the axes will not be given. You choose a set of Cartesian coordinate directions and then you end up with a plane state of stress. But we will use the axes given in the problem. This is the x-axis, axis of symmetry. Vertical axis, the y-axis, and then the third orthogonal axis is this thing. Forces acting on the free end, one along the x-axis of magnitude 100 newtons, and then one along the negative y-axis, 200 newtons. There is a point or 2 points of interest actually on the fixed end of the shaft. They are points A and B. And that's point A, and then right at the top is point B. What are we going to do in this problem? At points A and B, we need to obtain the principal stress values, the maximum in-plane shear stress values, and then draw the orientation of the area elements. Okay, so at A and B. principal stress. Maximum inclined shear stress. And then draw these on a area element with proper orientation. Draw these on an area element showing proper orientation. Okay. And if you want, we can, not going to talk about material behavior, but if you want, we can think of this as a ductile material just for simplicity. Which means the shaft is made of steel or aluminum or one of those kinds of ductile materials. And if you have a ductile material, the method of failure is due to shear stresses. Okay? The question is, okay, what's important about points A and B? Perhaps somebody has done an experiment and figured out, okay, most probably failure is going to be initiated at one of those 2 points. Which point could it be? Okay? We will not go into the details of how the failure is initiated and the failure theories that go with it, but these are the steps that you take before you hit the last part, which is the failure theories part, which is not a part of ME 2020. Okay? Alright, in solving this problem, you obviously have to figure out the internal forces and moments at the fixed end of the shaft. So typically, as I said, I will draw a line sketch and then sum the moments and the forces at the fixed end. Okay, so line sketch. I'm going to draw the axis of the shaft. And then I have the Y and the Z axis at the back end. So this is the Y, X, and Z. So let's say that I'm drawing these at the point C, which is a centroid. Okay, and A and B are on the Y and the Z axes respectively, as you can see here. On the other end, I have the 100 Newton and the 200 Newton force. Distance from where the force is acting to where the y-axis is, or which is the cross section at the fixed end, is going to be 2 meters, which we know, we're told. On the fixed end, which is where the axes have been drawn, you mark the support reactions and then the reaction moments. Okay, so I'm going to have Nx, normal force along the x-axis. I'm going to have Vy and Vz, shear forces. Vz. Vy. Okay, and then I'm going to have a torque, a reaction torque, which is the internal torque at the fixed end of the shaft along the x-axis. Tx, which is obviously 0 in this problem. Okay, then I'm going to have the bending moments. So the Z, Mz, and then one more about the y direction. Any questions so far, please? This is what we have done for combined loading problems, so this is not anything new. The new things will happen in once we are done with the analysis at the points A and B using the area of combined loading. Okay? I'm not going to spend too much time obtaining the support reactions because this is just summation of forces, summation of moments. So if I sum forces in x, y, and z, I end up getting the following. A sum of forces Nx is going to be equal to 100 newtons. There is no shear force along the z direction in terms of the applied forces, so Vz is 0. Vy is 200 newtons, okay, pointing up. Sum of moments will give me the reaction moments, where My and Mz are bending moments, and then Tx is the reaction torque. Tx is 0 because all these forces are acting at a point on the x-axis. Okay, so their line of action passes through the axis of interest, so Tx is 0. Am I making sense to everybody? Okay. What about Mz and My? Look at this. If I'm trying to find My, I'm summing moments about the y direction. The 100 Newton force has a line of action intersecting the y-axis, does not cause a rotation. The 200 Newton force is parallel to the y-axis, does not cause a rotation about the y-axis, so My is going to be 0. Then we do the same thing for the z direction. Mz, 100 Newton force, has a line of action intersecting the z-axis, so that is not going to cause a rotation about the z direction. Then I'm going to have this 200 Newton force. It is not parallel to the z-axis, its line of action is vertical here. So that's obviously not intersecting the z-axis either, so that's going to cause a rotation. Right hand rule, fingers of my right hand aligned with the force. My hand fingers pointing down, my palm faces the axis z. I curl my fingers. This is going to cause a positive rotation about the z direction of magnitude 200 times 2 newtons. Okay, so I can mark it out here and say times 2 Newton meters. Is this clear to everybody? And obviously you see that Mz is directed along the positive z. This is also directed along the positive z, so Mz has to be minus 400 Newton meters. Sum of moments about the z-axis is 0. So straightforward so far. Right? Most problems are going to be in this similar manner. It is all just a sum of force, sum of moments. You do the statics. Once you're done with the statics, you start doing the mechanics. Yes.
Why is it negative?
Because you see, if I'm summing moments about the z-axis, this is along the positive z, this is also along the positive z. And they add up to 0, which means this has to be negative. Okay? Make sense to everybody? Alright. Moving on to the next step is now you're going to view the cross section from the back end here. Take that, flip it towards you, you're going to see a two-dimensional circle. Okay. Vertical axis is the y-axis. The axis that is coming out of the page is the x-axis, which is coming towards you. And then I'm going to have the z-axis, obviously, along the left. This is the centroid C. Then my points of interest. The point A is along the positive z-axis, so here is my point A. And then I'm going to have point B at the outermost circumference right here. B. These are my points of interest. Then I draw the reaction forces and reaction moments which we calculated. There's going to be Nx, I'm sorry, which is 100 newtons. Then I'm going to have a Vy pointing in the vertical direction, which is 200 newtons. No torque, life is simple. There's no moment about the y-axis. There's going to be a moment about the z-axis, which we found out was negative because of the fact that if I add this and add that, it has to give me 0. Okay? So since it is negative, I'm going to mark it along the negative z-axis, but without the negative sign. So watch this. Mg is now plus 400. Any questions so far? Okay. Now all we have to do is figure out, okay, what are the stresses at the point A and what are the stresses at the point B. Because of the fact that you have a normal force, the normal force is going to exert an average normal stress at each and every point on the cross section. Okay, so that's going to be common for all the points. So I'm going to write this down. In the meantime, I'm going to push this thing up. Is everybody good to go? Okay, including my cinematographer. Too high? Yes, yes, question.
For the MZ, could you have drawn it going the same direction as the positive z-axis with the same counterclockwise rotation? Or
But I have to call it as minus 400.
You would have to, okay.
Right. Right. So rather than call it as minus 400, I just flip it. Call it as plus 400, but along the negative series.
Okay.
Okay. So at the point A, let's start off with point A. What are all the stresses? Okay. Is everything okay? At the point A, what are the stresses? I'm going to have a normal stress due to the normal force. So I'm going to have sigma xx. It's the xx direction, right? The subscript for the normal stress at the point A is xx because of the fact that the normal force is along the x-axis. The subscript for normal stresses will be the same in both the indices. Okay? So sigma xx at the point A, there's going to be a contribution from the normal force. So this is nx divided by the area of cross section. This is going to be tensile. Because of the fact that the normal force is pointing out. Then, do I have any contributions from the bending moment mz? For the point A is on the bending axis, which means that the bending moment is not going to cause any stresses at the point A. Okay, so there is going to be no contribution from the bending moment mz. And so if I do the calculations, this is going to end up being the following: 0.32 megapascals, 100 by pi times r square. By 1,000 square, so around 0.32. Megapascals in tension. Okay? And in the meantime, can somebody quickly check this number, because I feel like I have something there. But I'll continue with calculating the shear stresses at the point A. Okay, so tau at the point A. Now, the directions for the shear stress. I'm going to have the shear force pointing in the y direction. The area normal to this cross section is the x-axis, so which means that the indices for my shear stress is going to be yx. And this is by definition dq by it. Vy q, neutral axis t suffix tau. What are all these quantities for us? Vy is 200 newtons. Maybe I'll just do a quick sketch here. This is Vy. T suffix tau is going to be 2 times the diameter, 2 times the radius, starting from here, all the way to there. This is T suffix tau. Then to calculate Q, I either look at all the area above the point A or below the point A. Yes, sir, question.
Yeah, Professor, instead of 0.3 megapascals, it's
795.79.
0.7. So let's say 0.8. Okay, thank you. 0.8. No, thank you. Q, to calculate Q, I'm going to look at the area above the point A. Okay, this is stuff that we've done before, but I'm just revisiting it once again. Then this is going to be A prime, which is pi by 2 r square. I need to find the centroid and find the distance of the centroid of the shaded portion from the neutral axis. This is the neutral axis. If I have a shear force, the neutral axis on the plane is the direction perpendicular to the shear force. In this case, the z-axis is a neutral axis for the shear force. If I have a bending moment, the axis of bending is a neutral axis for the bending moment. Okay, once again, this is old stuff. Locate the centroid. Which is y bar prime, which is 4r by 3 pi. Okay, combine them all together. So this is going to be the following. So this is 200. Multiplied by q, which is y bar prime times a prime. So q. And that's going to be, if you do the math, it's 2 by 3 r cube. Okay? So 2 by 3 and 3, 1000 cube. Okay, it is just a combination of those two. The pi's cancel off. There's a factor of 2 in the denominator, a factor of 4 in the numerator, so I get 2 by 3. R square times r is r cube. Okay? This is pi by 4, r to the power 4, moment of inertia of a circular cross section. So this is to the power 4, multiplied by t suffix tau, which is 2 times r. And I believe my number on this is right. This is around 2 megapascals. Direction of the shear stress, very important, because you've got to draw the area element and the volume element as well. So I first draw an area element at the point A. The direction of the normal stress is going to be pointing out of the page, so it's tensile. That is sigma xx at A. The direction of the shear stress is going to be pointing in the direction of the positive y direction because of the fact that the shear force is acting vertically up. And I don't have a torque acting in this torque. Okay? So this is just going to be pointing. So this is tau yx at the point. Fx value here is 0.8.
Oh, Professor B?
Yes, sir.
I think that one's actually 0.08.
0.08.
Yeah.
Very good. Let's say 0.1.
You had one job.
And as you will see, these values are very insignificant. The major danger to any body is bending stress. This is just going to be a minuscule number. This creature is also, for all that hard work calculating y bar prime, q prime and all those damn things, this is going to be pretty small compared to your bending stress values. The major culprit always is bending. Okay? Okay, I'm going to clear up this panel here. And then draw the volume element. And then using the volume element, we will impose upon a plane state of stress, sketch out the Mohr circle, compute the principal stresses, which tells you that each and every point on the body will have an associated principal stress. Point A will have one, point B will have one, point C will have one, some other random point will have another one. When a body fails, let's say if it's a brittle body, you have to figure out which point on this body has the largest of those principal stresses. That is the trick. Which is why I am choosing 2 points here judiciously, trying to figure out, okay, which one is going to cause major damage. I'm going to clear this one. Draw the volume element. Okay. Remember your axes. This is the x-axis coming out. Okay, the z-axis is pointing to my left, as you can see from the figure up there. So my volume element now. Before I draw the state of stress on the volume element, I first set up my axis. Vertical axis obviously is the y-axis. The face that I'm viewing is this particular face, which means that the x-axis is going to be perpendicular to that particular face. The axis that is perpendicular to that face is my x-axis. Is this okay with everybody? Everybody understanding? Alright? Okay, axis perpendicular to that is the x-axis. Obviously the remnant is the z-axis on the other side. Okay? So this is the negative z. The positive z-axis is on the other side of the dotted line. I don't want to clutter my figure, already it's cluttered. Then I draw my sigma xx, my tau xy. Sigma xx. Front face, back face. At the point A. Then I have my tau xy, which is going to be a complementary state of stress. If I have a shear stress on one face, it's going to cause shear stresses on 3 other faces, 2 of them being orthogonal to each other. So one up, back face, top face, bottom face, all of them being the same magnitude. And if I have tau ix, it's the same as tau xy, because tau ij and tau ji are the same. And mind you, this is only for solid bodies, not for fluids. Things change when you go to fluids. It's the dark sciences. It's magic. Okay. This is clearly not a plane state of stress because I'm seeing a 3-dimensional volume element. So here is what you do to convert it into a plane state of stress. You set up a viewpoint. I'm going to set up a viewpoint on the positive z-axis side. So view from here. If I view it from there, I'm going to switch this volume element into an area element, okay, which I'm going to draw in this particular panel.
Does it matter where you take the view versus the left?
Usually it doesn't matter. I just want this fellow to be on to my right. So if I view it from this back face of this cube, this is going to be on my right when I draw the rectangle. If I view it from here, this is going to be to my left. Kind of awkward to see the things. Okay, so plane state of stress from the view. X-axis, my y-axis, okay? Clearly sigma xx is along the positive x-axis, so sigma xx sigma xx. Watch this. This face here, which is the shaded face, becomes this side. Okay, so once again, this is the shaded face. And it becomes the side which I am showing now. But the shaded face is no longer a three-dimensional body, it is just a single line because you are viewing it from the front side. Okay, the front viewpoint. Which means the direction of the shear stress is pointing up. That is important for me. This is going to be tau xy at the point A. If I know that one creature, I know everything else on the other sides. Points down, this way, this way. Keep in mind your sign convention. For stresses, plane stresses, okay? This is the sign convention. If this is my y-axis and my x-axis, then if the shear stress is pointing on the positive y on the x-axis face, that's considered a positive shear stress. Okay? This is tau xy. If the average normal stresses or the bending stresses combine together, which cause a normal stress if they are tensile, they are positive on both faces. Likewise, sigma y is positive. So according to our sign convention, tau xy is now going to be plus 2 megapascals. I just erase the value, but it's going to be plus 2 megapascals because it aligns with the sign convention. Sigma xs obviously is tensile, so not much of thought required for that. This is going to be 0.1 megapascals. For all practical purposes, it is worthless. You can just discard it. We will still keep it, of course. But in reality, nobody worries about it. It is difficult to pull something and break it. It is easier to bend something. Alright, I'm going to get rid of this figure here so that we end up drawing a Mohr circle. I want to do it at point A. We'll complete it today. We'll come back and polish off point B on Monday. And I'll continue solving problems of this nature and introduce you to the strains in 3D as well on Monday. Okay. Why do I need to draw the Mohr circle? I need to figure out the principal stresses and the maximum in-plane shear stress at point A. So to obtain principal stresses, I'm going to push this creature up a little bit. Casting a shadow upon the proceedings. Okay, Mohr circle. On my face of interest, okay, so this is the side of interest. We figured out together that based on the sign convention, these are all positive values. So I first write down the center of the Mohr circle. So C for the point A is going to be sigma xx plus sigma yy by 2. Comma 0. Okay. And sigma yy is 0. Sigma xx is 0.1. So this is 0.05 megapascals and 0. So many megapascals. Then I have the point of interest. Okay, that is the stresses on the face that I've called as the interest. So we typically call that as A. You remember from last time the point A on the Mohr circle. The subscript here represents the fact that I'm doing this for the point A on the cross section. Okay? For the point A, sigma xx and tau xy. According to our sign convention, both of them ended up being positive, so I just put them as positive letters. So this is going to be 0.1 and then 2 megapascals. One can calculate the radius of the Mohr circle. Is the distance from point C to point A. The segment length, which is the square root of the sum of the squares of the individual coordinates, Euclidean norm. So there's going to be 0.1 minus 0.05 square plus 2 minus 0 square. 4 to the power 1 by 2. 0.1 minus 0.05 is 0.05. 0.05 square plus 2 square is just essentially 2 square. So this is approximately going to be equal to 2 megapascals. Maybe 2.03 or something like that. Okay, any questions so far, please? So whenever you do Mohr circle, you need 2 points and then one distance. Okay? The point C, which is the center, the point A, which is your point of interest, which comes from your planar state of stress. Then you find the length of this side, CA, which is nothing but the radius of the Mohr circle. Then you draw the Mohr circle itself. Axes. Plus sigma. And plus tau. If it is okay with everybody, can I draw the Mohr circle here? I'll just clear off the middle panel because it's a little larger space. Okay, so plus tau plus sigma, why is sigma positive in the negative vertical direction? Because of the fact that only if you do it will the Mohr circle give you results that are consistent with the derivations. Okay? This is just a graphical technique. Mark the origin O 0, 0. Then you mark the center of the circle, which is 0.05 and 0. So exaggerated distance, of course. This is C suffix A. Then I mark the point A itself, which is going to be 0.1 and then 2. So 0.1 along the positive, 0.2 and 2 megapascals along the positive tau. Okay, so it's going to be somewhere here. So this is going to be point A suffix A. Then you draw the radius, which is from point C to point A. Draw a vertical line, not a vertical line, a line, straight line. That's going to be my radius, and then using that as a radius, using the point C as the center, you draw the Mohr circle. I kind of messed it up, but let's see. You get the basic idea, you have to draw a circle. Okay? So I'll just draw a freehand circle, which is I think better than what I might have. Okay, so this is your Mohr circle. This is your origin. This is the point A suffix A, which is a critical point. And now, we got to start doing things here. Alright. I'm going to draw a vertical line passing through the point C suffix A, which is the center of the Mohr circle. That's a point that I'm interested in, where it intersects the top and the bottom. Then I'm interested in this point here, and this point here as well. So those are the diametric points that I'm interested in. From the origin all the way to the rightmost point is going to be your sigma 1 value. Okay. Then from the origin all the way to the second point of intersection on the horizontal axis is sigma 2. Let's calculate sigma 1 and sigma 2. I'm going to get rid of this panel here. Alright, to calculate sigma 1, it is essentially going to be the distance all the way from here to there plus the radius, right? So this is the radius. Sigma 1 is going to be the distance where the center is, which is CA. So that's whatever was it, 0.05 megapascals. Plus the radius, which was approximately 2. So sigma 1 is approximately 2.05 megapascal. This is positive. Does this make sense to everybody? Distance from point O to point C, the origin to the point C, was the center location that we calculated as sigma xx plus sigma yy by 2, which was 0.1 divided by 2, which is 0.05. Then distance from point C to any other point on the outermost circumference obviously is the radius. That's going to be 2 megapascals approximately, which we calculated. Sigma 2 is a little more tricky. You first have to recognize, is sigma 2 on the positive or the negative sigma axis? It is on the negative sigma axis. So put a negative sign, first thing, right? Because this is a negative sigma axis. Put a negative sign, calculate the distance. It's going to be from here all the way to that point, which is nothing but the radius minus whatever is the distance of point O to point C. Okay? That's going to be the radius.